Hey guys, welcome to Learn Today IGCSE. This video is a tutorial for Chemistry Paper 6, Variant 6-2 from February-March 2024 examinations. Question 1. Calcium carbonate is an insoluble solid. Calcium carbonate can be made by adding excessive aqueous calcium chloride to aqueous sodium carbonate. A student makes a sample of calcium carbonate. The first two steps of the method are shown in Figure 1.1. In Step 1, excess aqueous calcium chloride is being added into the aqueous sodium carbonate, and in Step 2, the mixture is being stirred. Question A. Name the item of apparatus labeled A in Figure 1.1. To name the apparatus in your Chemistry Paper 6 is a very common question, so make sure you know the list of apparatus beforehand. An apparatus here is called a glass rod or a stirring rod. Next, question B. Suggest why the mixture is stirred in Step 2. So in Step 2 here, we are using the glass rod to stir the mixture. This mixture now contains ions from calcium chloride and ions from sodium carbonate. So we are going to have to allow these reactants to collide with each other, therefore speeding up the rate of reaction. Next, question C. After Step 2, the student filters the mixture to remove the solid calcium carbonate formed and collect the filtrate. Draw a labeled diagram to show the apparatus used for this filtration. So to filter the mixture out, we're going to need a filter paper. And to collect the filtrate, we're going to need a conical flask. So the solid calcium carbonate formed will be collected over here, and the filtrate, which is sodium chloride, will be collected in the conical flask. So this here is a solid, which is our residue, and this is an aqueous solution, which is liquid, will be collected in the conical flask as the filtrate. Next, question D. The solid calcium carbonate obtained by filtration is not pure. Part 1. Identify one substance other than water which is mixed with the calcium carbonate and makes it impure. This question was exactly asked from also October-November 2023 paper 6. So as you can see, past year questions are always repeated, so it's always a great idea to practice as many papers as you can. So we are being told that the calcium carbonate that is being formed here is not pure, meaning that it's not 100% calcium carbonate. It also has impurities such as water. Since this filtrate was separating NaCl and calcium carbonate, there might be a little bit of sodium chloride found in the residue. So you can mention any one of these for 1 mark. Part 2. Describe how the substance you have identified in D Part 1 can be removed from the calcium carbonate. So to remove the impurities like sodium chloride out of the residue from here, what we can do is pour more water on top of the residue to wash off whichever NaCl that is formed over here. So this way we can get a more pure form of calcium chloride. Next, Part E. Describe a test the student can do on the filtrate obtained in Part C. The filtrate is sodium chloride to show that the calcium chloride used is in excess. Give the result the student obtains if the calcium chloride is in excess. So we're looking to find what kind of test that can be done for sodium chloride to see if calcium chloride is in excess. Sodium chloride is the product of when calcium chloride reacts with sodium carbonate. If the calcium chloride was in excess, it means that all the sodium carbonate has been completely used up during the reaction. Therefore, what we can do is test for carbonate ions. So why are we testing the presence of carbonate ions is because we want to check whether or not there is any carbonate ion present. If this was in excess, it tells us that there should be no carbonate ion present anymore because it was completely used up. So we can do this by adding hydrochloric acid and check if there is any effervescence in the result. Why are we looking for effervescence is because carbonate ion will produce carbon dioxide gas. And since this is gas, we can look for bubble or effervescence. So if this was in excess, it means that all the sodium carbonate is used up, so no carbonate ion should be present, therefore no effervescence will be formed. Question 2. A student investigates the reaction between aqueous sodium carbonate and 2 different solutions of dilute hydrochloric acid labeled A and B. The student does 3 experiments. Experiment 1. Rinse a burette with distilled water and then with hydrochloric acid of A. Then rinse a conical flask with distilled water. Fill the burette with dilute hydrochloric acid A. And then you're going to run some of the hydrochloric acid out of the burette so that the level of the dilute hydrochloric acid is on the burette scale. And then we're going to record the initial burette reading. And next part, you're going to use a measuring cylinder to pour 25 cm cube of aqueous sodium carbonate into a conical flask. Then add 5 drops of methyl orange indicator into the conical flask and stand the conical flask on a white tile. So the setup is going to look something like this, and we're going to slowly add the hydrochloric acid A from the burette, which is over here, into the conical flask while swirling the flask until this solution turns to become orange. When it turns to become orange, the hydrochloric acid in here would reduce and we're going to record the final burette reading. And then in experiment 2, we're going to perform the same exact experiment with the same acid. The only difference here is that we're going to use 5 drops of thymophthalate indicator instead of methyl orange indicator. And for experiment 3, we're going to repeat experiment 1, but instead we're going to use dilute hydrochloric acid B. Question part E. Use the burette diagrams in figure 2.1, 2.2 and 3 to record the readings for experiments 1, 2 and 3 in table 2.1 and complete the table. So here is table 2.1. So we need to measure the final and initial burette reading. The initial burette reading here is 0.8. This here is at 26.2. And then we've got over here 0.2, and this is 1 above 13, so it will be 12.9. And then we've got exactly at 1, and this is 1 below 39, so it will be 39.1. So we'll just fill into the table accordingly. Next, you're looking to find the volume of dilute hydrochloric acid that is being added. To do this, we will look for the difference of the initial burette reading and the final burette reading. So whichever that has been reduced is the volume for the dilute hydrochloric acid being added into your conical flask. Question B, part 1. State which solution of dilute hydrochloric acid A or B is the more concentrated. Explain your answer. So in experiment 1, we were using hydrochloric acid A, and in experiment 3, it was hydrochloric acid B. Even though in experiment 1 it was hydrochloric acid A, the only difference between 1 and 2 is that we were using a different kind of indicator. This was methyl orange, and in 2 it was thymophthalate. In the first experiment, 25.4 cm cube was required to neutralize the base. However, in experiment 3, 38.1 cm cube of acid was required to neutralize the base. So we can conclude that hydrochloric acid A is more concentrated because only a little volume or a smaller volume was required to neutralize the base. Next question, part 3. Deduce how many times more concentrated this solution of dilute hydrochloric acid is than the other solution of dilute hydrochloric acid. So we can do this by comparing the volume of the acid needed. So we can take 38.1 over 25.4, which gives us a ratio of 1.5. This means that hydrochloric acid A was 1.5 times stronger than hydrochloric acid B. Next, question C, part 1. Compare the volume of dilute hydrochloric acid A used in experiment 1 to the volume of hydrochloric acid A used in experiment 2. The hydrochloric acid used in experiment 1 is 2 times more than in experiment 2. So we can just mention that the volume of HCl in experiment 1 is 2 times greater than in experiment 2. Part 2. Deduce the volume of hydrochloric acid B required to reach the endpoint if experiment 3 is repeated using thymophthalate indicator instead of methyl orange indicator. We can easily solve this using our mathematical skills. When used methyl orange, it was 25.4, and using thymophthalate, it was 12.7. So it decreased by half, meaning that if we repeat the same experiment for B using thymophthalate, the same thing is going to happen whereby it will reduce by half. So 38.1 divided by 2 is going to give us 19.05. Since these are all in one decimal place, I will write this as 19.1. And since this is looking for volume, don't forget your unit centimeter cube. Next, question D. At the start of experiment 3, the burette is rinsed with distilled water and then with dilute hydrochloric acid B. Part 1. Identify the substance removed from the burette when it is rinsed with distilled water at the start of experiment 3. Experiment 3 was performed after experiment 2, whereby the burette was filled with dilute hydrochloric acid A, meaning that we are trying to rinse off the hydrochloric acid A from the burette. Next, part 2. Describe how the result of the titration would change if the burette was not rinsed with dilute hydrochloric acid B after it had been rinsed with water. If we hadn't rinsed the burette, it will still contain a little bit of hydrochloric acid A. So it's going to change the amount of hydrochloric acid needed to neutralize the base. And now we're going to require more hydrochloric acid of B to neutralize the base. Next, question part 3. Explain why the conical flask is not rinsed with aqueous sodium carbonate after it is rinsed with water. So the reason we don't do that is because we do not want to change the fixed volume of sodium carbonate inside the conical flask. If we rinse it with sodium carbonate, there might still be a little bit of sodium carbonate inside the conical flask, and that will then increase the volume of sodium carbonate. Next, question E. Explain why a white tile is used during the titration. As you can see, the beaker here is being placed on top of a white tile. Since this question is to observe a color change, placing a white tile is going to make it easier to see when the color change happens. Next, question F. Describe the effect on the result of warming the aqueous sodium carbonate used in experiment 1 before carrying out the titration, and explain your result. When warming a solution, it increases the kinetic energy of the particles, which then leads to a faster rate of reaction. In this experiment, the result is the color change. Increasing the rate of reaction will only speed up the reaction, which means that the time taken will be shorter. But the time taken here is not the result that we are looking for. We are looking to find the color change. This means that there will be no effect on the color change if we warm up the solution. The only way to see a color change is if we change the number of moles or the volume for the sodium carbonate. Question 3. A student tests two substances, solid C and solid G. Test on solid C. Solid C is ammonium iodide, so it must consist of cation ammonium and iodide anion. The student dissolves solid C in water to form solution C. The student divides solution C into 3 approximately equal portions. Complete the expected observations. These types of questions are related to your anions, cations, and gases test. Question A. To the first portion of solution C, the student adds about 1 cm³ of dilute nitric acid followed by a few drops of aqueous barium nitrate. Adding dilute nitric acid and then aqueous barium nitrate is to test for the presence of sulfate. And if there is a presence of sulfate, there will be white precipitate present. Since solid C is containing ammonium and iodide, this means that there are no sulfate ions present. So there will be no changes for this test. Question B. To the second portion of solution C, the student adds about 1 cm³ of dilute nitric acid followed by a few drops of aqueous silver nitrate. Adding nitric acid and silver nitrate is a test done to test the presence of halides. This solution contains iodide and ion. This means that you will see a yellow precipitate. Next, question C. To the third portion of solution C, the student adds an excess of aqueous sodium hydroxide. Adding aqueous sodium hydroxide is a test for cations. The cation present in this solution is ammonium, and when added sodium hydroxide, it says that ammonia is produced on warming. However, in this test over here, the solution is not being heated. That means there will be no ammonia produced. Hence, there will be no changes in the observation. Part 2. The student warms the product formed in C Part 1 and tests any gases given off. Now the student warms the product. So upon warming, there will be ammonia produced. we can use a red litmus paper to test the gas produced. And the observation is that the red litmus paper will turn blue because this is an alkaline product. You have to remember the observation for each indicator in acid, alkaline, and neutral solution. So for ammonia, since it is an alkaline, it will turn a red litmus paper into blue color. Next is test on solid D. Table 3.1 shows the test and the student's observation for solid D. Test 1. To do a flame test on solid D, the observation is that yellow colored flame is observed. If a yellow flame is observed, this tells us that sodium ion is present. Next, test 2. Gently heat about half of the remaining solid, and the observation is that steam is given off and condensation forms at the top of the boiling tube. If steam is given off, that means water is present. And hold a strip of anhydrous cobalt chloride paper at the mouth of the boiling tube. The anhydrous cobalt chloride paper will change color. Now, anhydrous cobalt chloride is blue in color. However, when there is a presence of water, it will turn into pink. So, since there is water present here, the anhydrous cobalt chloride will change color from blue to pink. Test 3. Dissolve the remaining solid in water to form solution D. Divide solution D into 3 portions. To the first portion of solution D, add aqueous ammonia drops-wise until in excess, and a green precipitate which is insoluble in excess will be formed. Okay, so the effect of adding aqueous ammonia, it is mentioned that you will observe a green precipitate. So there are 2 possibilities here because green precipitate mean that could be presence of chromium or iron 2+. So this tells us that solid D either consists of chromium 3+ or Fe2+. Next, test 4. To the second portion of solution D, add a piece of aluminium foil and about 5 cm³ of aqueous sodium hydroxide, and a green precipitate is observed. Adding aluminium foil and then aqueous sodium hydroxide is a test for anion to test the presence of nitrate. And then heat the mixture formed and hold damp red litmus paper at the mouth of the boiling tube. The red litmus paper remains red. If a red litmus paper remains red, this means that the solution is acidic. Adding piece of aluminium oxide and sodium hydroxide is to test the presence of nitrate. If there is nitrate, ammonia would be produced, which is an alkaline solution. And over here, if the solution is acidic, this tells us that there is no ammonia ion present in this solution. Next, test 5. To the third portion of solution D, add about 5 cm³ of dilute nitric acid. Bubble any gas formed through lime water. So effervescence tells us that there is gas produced, and when the gas is bubbled through lime water, the lime water becomes milky. This tells us that the gas produced is a carbon dioxide, which most likely comes from diluting nitric acid with a metal carbonate. Okay, question D. State the final color of the cobalt chloride paper in test 2. So as mentioned previously, the cobalt chloride paper will turn from blue to pink. So the final color here is pink. Question E. State what ion in the observations in test 4 show is not present. In test 4, we have learned that there will be no ammonia present. Next, question F. Identify the gas produced in test 5. In test 5, we have identified that carbon dioxide gas is produced. Next, question G. Identify the 3 ions in solid D. So the 3 ions are sodium, either chromium or iron 2+, and we also have found out that there must be carbonate ion present because carbon dioxide was produced. Next, question 4. When excess dilute sulfuric acid is added to solid zinc, hydrogen gas and aqueous zinc sulfate are made. And this is the equation given. You are required to plan an experiment to show that copper is a catalyst for this reaction. Your plan should include how the results of the experiment will show that copper is a catalyst for this reaction. You are provided with zinc powder, dilute sulfuric acid, copper powder, and common laboratory apparatus. Planning an experiment. You're going to need lots of practice for this. Keep trying as many past year questions as possible, and we'll try to stick with a technique or format to answer these types of questions. We want to prove that copper is a catalyst. A catalyst is something that speeds up the reaction without being used up. So we know now that this experiment here is testing the rate of reaction. In the reaction, we can see that hydrogen gas is being produced. So the volume of hydrogen gas here can be used to identify the rate of reaction. If higher volume of gas is produced, this means that higher rate of reaction is present. So we're going to use the volume of gas to determine the rate of reaction with the presence of catalyst and another one without the presence of catalyst. So we're going to prepare dilute sulfuric acid and then add in zinc powder into it. Hydrogen gas will be the product of this reaction, so we're going to use a delivery tube to collect the gas produced. We can observe the number of bubbles produced in, let's say, 1 minute and record this data. And then we'll repeat this experiment again, but this time we're going to add the catalyst, which is the copper. So we're going to have to state how much of copper that is being used, let's say 10 gram. And now we're going to record the number of bubbles produced in 60 seconds. So we can compare the number of bubbles produced when there was catalyst used and no catalyst present. Since copper is a catalyst and catalyst speeds up the reaction, we should observe a higher number of bubbles produced when the copper catalyst is being added into the reaction. And catalyst is a substance that is not used up during the reaction. So we also have to prove that the copper was not used during the reaction. If we are using 10 grams of copper at the beginning of the reaction, we should weigh the copper at the end of the reaction and make sure that it is also 10 grams. So this will prove us that copper is indeed a catalyst. So let's write all of this into our answer space. So for the preparation, you're going to measure 20 centimeter cube of dilute sulfuric acid and 10 gram of zinc powder. Make sure to mention the volume and the mass that you are using during any experiment performed. You're going to connect a delivery tube into the inverted jar to collect the gas produced. So this is the setup of the experiment. And what you're going to observe is the number of bubbles produced, and you're going to repeat it with 10 grams of copper powder this time. Again, don't forget to mention the mass that is being used. And lastly, you're going to filter the copper powder to weigh the mass, because we need to prove that copper is a catalyst and catalyst will not be used up at the end of the reaction. So if the number of bubbles produced is higher and the mass is the same at the end of the reaction, this means that the copper is a catalyst. Alright, thank you for watching, guys. That's all for this video. For the next video, I'll be discussing on Physics Paper 2. If you found this video helpful, please subscribe to my channel. Thank you. Bye bye. Take care.